Welcome to the 3Dflow Academy. In this video, we'll look at the basic workflow to create a 3D model from drone images. We'll cover all 4 stages of the 3D reconstruction, including model scaling and georeferencing using ground control points. For this tutorial, we'll use a dataset captured with a DJI Matrice 300. It includes both nadir and oblique images with RTK coordinates, acquired with a full-frame DJI P1 camera, for a total of about 340 photos. As you can see, before capturing the images, a few targets were placed on site. Their coordinates were measured with GNSS equipment, so we can scale and georeference the 3D model. Let's start by selecting the folders and drag and dropping them into a new Zephyr session. At this stage, Zephyr lets you choose what you want to generate: the camera orientation and sparse cloud, dense point cloud and mesh, textured mesh, and, if needed, even ortho photos. Then click Next in the new project wizard. Click Next again to reach the Import Constraints window. Zephyr automatically detects RTK coordinates in the images and assigns them a higher accuracy level compared to the default one used for standard GPS coordinates. At this stage, we can set the reference system that will be assigned to the sparse cloud at the end of the image orientation step. From the reference systems database, you can find the one you need either by scrolling the list or using the search tool and then click OK when you're done. It's worth noting that bundle adjustment, the algorithm used to optimize camera positions, is enabled automatically because RTK coordinates are considered reliable enough to be included in the optimization. In the next screen, we can set the category, meaning the subject type of the 3D reconstruction, and the reconstruction preset. For this project, we select the category Aerial Nadiral Pictures and the default preset. Before starting the computation, you can check the distribution of the GPS positions on the map. Then click Run to start processing. When the first step is completed, Zephyr reports how many images were successfully oriented. Click Finish. Then you'll see the sparse cloud along with the image positions in the workspace. At this point, you can orbit and inspect the result, and check the sparse cloud properties either by double-clicking its name or right-clicking it and selecting Properties. It's good practice to enable the bounding box right after image orientation. The bounding box works as a selection tool. It defines a volume that tells Zephyr what to focus on during the next 3D reconstruction stages. Fitting the bounding box to the subject or the area you're interested in helps Zephyr optimize dense point cloud and mesh generation. You can translate, rotate, and scale it directly in the 3D workspace, or by using the editing panel that appears as soon as the bounding box is enabled. Another good habit is saving the project at the end of a reconstruction stage. After saving, Zephyr creates a .zep project file and a folder where all the 3D elements are stored. Now, let's see how to work with ground control points. There are 2 ways to add ground control points in Zephyr. The first method is clicking Import 3D in the Control Points panel. To do this, the current project and the coordinates you're importing must use the same coordinate system. In the Import dialog, click Browse to locate the .text or .csv file containing the coordinates. After selecting the file and clicking OK, Zephyr shows a summary table where you can review the coordinates you're about to import. Here you can also click on Easting, Northing, and Altitude if you need to swap the coordinate columns. Click OK to import the coordinates and add the ground control points to the project. If the workflow has been followed correctly, the GCPs will be distributed over the sparse point cloud, and they will also appear in the control points list. Now we need to link the GCPs to the project images. Click the first control point and select Edit. The editor opens with the image list on the left and the selected photo in the center. Notice that Zephyr already suggests the cameras where control points should be located. It also shows a red circle on the selected image indicating the approximate position of the control point. Add the same control point to at least 3 images. Using as many images as possible will help improve the bundle adjustment during the next model scaling step. When you're done, click OK to return to Zephyr's main interface. In the control points list, you'll see an initial metric error for that GCP. This is just a baseline value, and it will be refined after model scaling and bundle adjustment. Repeat the same procedure for all the GCPs imported into the project. Now we remove the GCPs from the project to show the second method to add control points in Zephyr. Click From Images in the Control Points panel to open the GCP editor again. Initially, Zephyr provides no suggestions, so you'll need to scroll through the image list to find the ground target where you want to place the control point. After marking it on the first image, Zephyr automatically suggests additional images where the GCP can be pinpointed, highlighting them on the list. Inside the GCP editor, you can also rename the control point before clicking OK. Alternatively, you can always right-click the GCP name in the Control Points panel and rename it later. Repeat this procedure for all the GCPs you want to add to the project, making sure the GCP names in the project match the coordinate labels you'll import. Use the left and right arrow keys to scroll through images while marking control points. Once that's done, click Align Model with 3D Constraints in the Control Points panel, and then click Import Constraints from File. Select the text or CSV file to import the point coordinates into Zephyr. In the next step, you can reorder the table columns as needed and select the coordinate system used to survey the ground targets. After clicking OK in the Align Using Constraints window, it's recommended to enable the bundle adjustment to optimize camera positions during scaling, and then click OK to start. Once scaling and georeferencing are complete, Zephyr shows a table reporting the final mean residual, the RMS error, and the residuals for each individual GCP and coordinate. You can reopen this table by clicking the Constraints Report button in the Control Points panel, or by going to the Tools, selecting Control Points, and then Show Alignment Info. Now, let's move on to the next reconstruction step. Go to the Workflow menu and select 3D Model Generation. Please note that the 3D Model Generation option lets you create a dense point cloud and a mesh at the same time. If you'd prefer to create them separately, select Advanced in the Workflow menu to access the steps individually. Here, you can set the category and preset for dense point cloud and mesh creation. For this specific project, we choose the category Aerial Nadiral Images and the High Details preset, and click Run to start processing. When it's finished, the dense point cloud and mesh entries are added to the project panel. You can inspect their properties at any time by double-clicking them or right-clicking their names. To check the surface geometry details, enable lighting in the workspace using the icon in the menu bar, and then click the icon next to it to disable color and view only the surface geometry. click the same two icons again to toggle back, re-enable color, and turn lighting off. At this point, if you want, you can generate an orthophoto. Go to Workflow and select True Orthophoto from Mesh. A bounding box aligned with the project reference system appears, together with the orthophoto wizard. Click Next to preview the orthophoto that will be created and to set parameters such as ground sample distance or pixel resolution. Click Next again to define export parameters, and then click Finish to start processing. When the process is complete, the DEM viewer opens automatically. Here you can see the orthophoto placed inside a map. In this case, the orthophoto color map depends on the altitude values, because the digital surface model is generated at the same time as the orthophoto. After closing the DEM viewer, you'll find the orthophoto and a new orthophoto entry in the project panel. Now we just need to create the texture. To do that, go to the Workflow menu and select Textured Mesh Generation. Zephyr lets you decide how many cameras to use for texture projection and which mesh to texture, and you can create multiple dense point clouds or multiple meshes within the same project. You also need to set a category and a preset for this final step. For the texture stage, categories and presets are slightly different compared to the previous phases, but Zephyr always provides a suggestion depending on what you chose. Click Next, then click Run to start processing. Once the final stage is complete, click Finish. The textured mesh appears in the workspace and is also listed in the project panel. Everything created in the project can be exported, and for each 2D or 3D element, you'll find multiple file formats and export options. Additionally, you can create and export a project report that includes all the information related to the project and its elements, including all details about the GCPs. And that completes the basic workflow in Zephyr with drone images. If you have any doubts or questions, feel free to contact 3Dflow technical support at support@3dflow.net.